Right now, the ground beneath one of the most densely populated coastlines on Earth is doing something that seismologists have not seen in this sequence, at this scale, in this specific pattern in the modern era of earthquake monitoring. 3 distinct earthquake swarms have erupted across Southern California in fewer than 60 days, and the word swarm here is not casual language. Each one is a cluster of dozens, in one case, hundreds, of individual earthquakes firing off in the same zone within hours or days of each other. 3 swarms, 2 months, 1 fault corridor, and the direction they are moving is not random. It is sequential. It is spatial, and it is precisely the kind of pattern that the most experienced seismologists in the country do not dismiss. What makes this moment genuinely different from the constant low-level seismic activity that California always produces is the convergence, not 1 signal, not 2. Every major metric that geophysicists use to assess earthquake hazard in a region is elevated simultaneously right now in August of 2026. 2 independent research teams working from opposite ends of the state, using completely different data sets and methodologies, published findings within the same summer that arrive at the same destination. The San Andreas fault system is more dangerous than the models assumed. More dangerous in the north because the fault is moving faster than scientists believed. More dangerous in the south because the stress load has reached a level not seen in 1,000 years. And threading through the middle of all of this, a fault that has not produced a major surface rupture in recorded human history is beginning to stir for the first time. In the modern era, that is the story we are walking through today. Not to generate fear for its own sake, but because the data is specific, the timeline is recent, and the implications are real for tens of millions of people. And right now, as this video reaches you, the 3rd swarm is still active. The Coso Volcanic Field in the southern Sierra Nevada is producing earthquakes as you watch this. The swarm that began on August 20th and 21st of 2026 has already grown to over 240 individual seismic events in a single week, with the largest reaching a magnitude 4.0. That number may not sound alarming in isolation, but the location changes everything. Now look at these 3 locations on a map, and the pattern becomes impossible to ignore. Swarm 1 struck at Fraser Park, the western terminus of the Garlock Fault, where it meets the San Andreas. Swarm 2 struck at Johannesburg, positioned along the central section of the Garlock Fault corridor. Swarm 3 is now active at the Coso Volcanic Field, sitting at the eastern edge of the same regional fault corridor, along the southern Sierra Nevada boundary. These 3 swarms are not random. They are marching eastward and northward along a connected stress pathway. They are following the architecture of the fault system itself, and that tells a very specific story about how stress is moving through the crust right now. When earthquake swarms occur in sequence along a connected fault corridor, the mechanism that links them is stress transfer. This is not a theoretical concept. It is one of the most well-documented phenomena in modern seismology. Every cluster of earthquakes that fires off in one part of a fault system redistributes the stress load onto the surrounding sections of crust. Some sections receive less stress after a nearby event. Those are called stress shadows. But other sections, particularly the locked fault segments that sit immediately adjacent to the swarm zone, receive additional stress loading. They become more pressurized, not less, after their neighbor moves. And the Garlock Fault, which sits at the center of this entire sequence of swarms, is a fault that carries an extraordinary amount of accumulated stress and has not released it through a major surface rupture in the entirety of recorded human history. The last confirmed major ruptures on the Garlock Fault are estimated at approximately 1050 AD near Tehachapi and approximately 1500 AD near Johannesburg. Both of those dates are before the European settlement of California, before the missions, before any written record of the land. The fault has been essentially silent for the entire span of modern civilization in this region. Its probable maximum magnitude is estimated between 6.8 and 7.6, meaning it is capable of sustained violent shaking for far longer and across a far wider geographic footprint. Right now, the recent history of the Garlock becomes deeply relevant to what is happening right now. After the 2019 Ridgecrest earthquake sequence, which produced a magnitude 6.4, followed by a magnitude 7.1 just 34 hours later, satellite radar imaging captured something that had never been recorded before. The Garlock Fault began creeping, slow aseismic movement along segments of the fault that had shown no surface motion in any prior observation period. The USGS noted at the time that the Ridgecrest sequence had increased the probability of a magnitude 7.5 or greater earthquake on the nearby Garlock Fault. That statement was made in 2019. Or now, in 2026, earthquake swarms are repeatedly activating zones that sit directly along the Garlock's trajectory. Swarm 2 struck near Johannesburg, one of the 2 locations where the fault's last prehistoric ruptures are estimated to have occurred. The stress signal is not subtle. This is where the 2 new research studies published this summer become essential to understanding the full picture. Because the swarm activity alone would be concerning. But the swarm activity layered on top of what these 2 independent scientific teams have now published is something else entirely. The first study was published on August 20th of 2026 by researchers at San Jose State University, led by geology professor Kim Blisnyuk. Her team spent years analyzing the Santa Cruz mountain section of the northern San Andreas Fault, focusing on displaced landforms at Sanborn County Park. They used high-resolution topographic mapping combined with a technique called beryllium-10 cosmogenic dating, which allows scientists to reconstruct fault movement over thousands of years by measuring how certain isotopes accumulate in exposed rock surfaces. The window this method opens is far longer than what conventional earthquake geology typically examines. Rather than studying the past 1,000 years of fault behavior, Blisnyk's team reconstructed 10,000 years of movement history along that section of the fault. What they found contradicted a foundational assumption that had shaped California earthquake hazard modeling for decades. The accepted model had held that as you move southward along the San Andreas through the Santa Cruz Mountains, the fault slows down because a portion of its motion bleeds off onto branching faults like the Hayward and the Calaveras. Under that model, the Santa Cruz Mountain section was expected to be accumulating strain more slowly than sections to the north. Slower accumulation means longer recurrence intervals between major earthquakes, which translates into lower assessed hazard. Levels in that zone. Planning decisions, building codes, insurance models, and emergency response frameworks were all built on top of that assumption. The study from the University of Hawaii contains one additional finding that demands specific attention. The stress configuration they modeled near the Cajon Pass junction, where the southern San Andreas and the San Jacinto fault systems come into close proximity, is structured in a way that raises the possibility of a rupture crossing that junction and involving both fault systems simultaneously. A joint rupture of that kind would not simply be the sum of what each fault could produce independently. The combined length of rupture, the combined stress release, the combined shaking duration would produce an event significantly larger and more destructive than either system could generate alone. The USGS scenario for a standalone magnitude 7.8 rupture on the southern San Andreas already projects nearly 2 minutes of sustained shaking across a corridor stretching from central California to the Mexican border with an estimated death toll of approximately 1,800 people, 50,000 injuries, and economic damage exceeding $200 billion. A joint rupture of the San Andreas and San Jacinto systems would move that scenario into territory that the existing models have not fully captured. The last major earthquake on the southern San Andreas Fault occurred in 1857, a magnitude 7.9 rupture that tore through central California along a fault segment that had been locked in accumulating strain for well over a century before it finally broke. That event happened 169 years ago. The tectonic plates that drive the San Andreas have not stopped moving in the time since. They continue grinding past each other at several centimeters per year, every year, without pause. Every centimeter of plate motion that occurs without a corresponding earthquake on the locked sections of the fault is another increment of elastic strain being stored in the crust. Another increment that will, at some point, be released. The physics of this process are not debated. The only question that remains genuinely open is timing. And timing at the level of specific dates is still beyond what earthquake science can provide. But the conditions that define elevated hazard, the measurable, quantifiable state of the system right now, those are not uncertain. They are the clearest they have ever been in the modern era of seismological observation. To understand why the current moment is unusual, even within California's long history of seismic activity, it helps to step back and look at the broader pattern. California's fault systems do not operate in isolation from the rest of the Pacific Rim. The Ring of Fire is a continuous, interconnected network of tectonic boundaries that encircles the Pacific Ocean, and energy redistribution across that network has historically shown correlations with major California earthquakes that are difficult to dismiss once you examine the record carefully. In 1906, 3 months before the Great San Francisco earthquake produced a magnitude 7.9 rupture on the northern San Andreas, a magnitude 8.8 struck the Ecuador-Colombia coast. That remains the largest earthquake ever recorded in that region. 3 months later, San Francisco. In 1952, the magnitude 7.5 Kern County earthquake struck Southern California in July. Earlier that same year, Japan had absorbed a magnitude 8.1 earthquake. And by August, a region of Tibet had been struck by an event estimated between 8.6 and 8.7. In 1868, several major seismic events preceded the Hayward Fault rupture. Of magnitude 6.8 in October of that year, including the largest earthquake in Hawaii's recorded history that April, a massive event near Arica, Peru in August, estimated between 8.8 and 9.1, and a burst of significant earthquakes across Ecuador and Colombia the same month. In 1812, a prolonged sequence of high-magnitude events on the New Madrid Fault system in the central United States, combined with major activity in Venezuela, preceded two major California ruptures within the same December. Now look at the Pacific in 2026. In June of this year, Venezuela experienced a significant double earthquake sequence along its major transform fault system. Seismologists have noted directly that Venezuela's fault structure and tectonic setting are mechanically analogous to the San Andreas. Both are transform faults. Both accommodate lateral plate motion in broadly similar structural settings. The comparison is not rhetorical, it is geophysical. Just days before this video was recorded, a major typhoon caused severe destruction across parts of East Asia. Hawaii absorbed the impact of Hurricane Ella. Multiple tropical storms are developing simultaneously across the eastern Pacific. Active cyclone. Systems are present in several ocean basins at once. The Pacific is in a state of extraordinary energy output right now, and that energy does not stay contained at the surface. Wave action, atmospherics, pressure loading, and the thermal expansion and contraction of the oceanic crust at plate boundaries are all real physical processes that affect the stress environment at fault zones where ocean meets continent. None of these factors independently triggers a major earthquake on a fully locked fault. But on a fault system that is already sitting at a 1,000-year stress maximum and experiencing active seismic swarms, they represent additional variables stacking onto a system that has very little remaining margin. The connection between extreme heat events and seismic hazard is not established at the level of direct causation. Scientists are careful about that distinction, and it is important to maintain it, but the physical processes involved in a major heat dome are not entirely disconnected from the stress environment in the crust beneath it. Thermal expansion of surface rocks and upper crustal layers, changes in groundwater pressure as aquifers respond to evaporation and recharge patterns, and variations in pore pressure within fault zones during extreme temperature events are all documented physical phenomena. Each one in isolation is insufficient to trigger a major earthquake on a locked fault. But layered on top of a system that is already at a 1,000-year stress high, experiencing active seismic swarms and sitting beneath a seismically active solar environment, each additional variable narrows the remaining margin further. This is the nature of complex natural systems approaching a critical threshold. No single factor causes the rupture. What causes the rupture is the accumulation of strain beyond the fault's capacity to hold it. What all of these converging signals indicate is that the system is closer to that threshold than it has been at any measurable point in the modern era of earthquake science. And the three swarms now documented across the Southern California fault corridor are not occurring in a vacuum. They are occurring within this specific convergence of elevated conditions. That context is what transforms them from a locally interesting seismic pattern into something that warrants sustained, serious attention from everyone who lives within the reach of these fault systems. The communities that would experience direct and severe impacts from a major rupture on the Garlock Fault alone form a geography that most people outside California do not fully appreciate. Mojave, Johannesburg, Tehachapi, and Fraser Park sit directly along the fault zone and would absorb the most intense ground motion in any rupture scenario. But the shaking footprint of a Garlock event at its upper magnitude range extends far beyond those communities. The San Fernando Valley, Santa Clarita, Lancaster, Palmdale, Ventura, Oxnard, and Bakersfield would all experience strong twos, very strong shaking. Edwards Air Force Base, Naval Air Weapons Station, China Lake, which sits immediately adjacent to the current Coso Volcanic Swarm Zone, and Fort Irwin National Training Center would all fall within the significant shaking radius. And that is the Garlock Fault in isolation, producing a rupture at its own maximum without any interaction with the larger systems surrounding it. The scenario that the University of Hawaii study specifically raises as a realistic, stress-driven possibility is the one that moves beyond individual fault behavior into what geologists call a cascading rupture. The stress configuration they modeled at the Cajon Pass junction, where the southern San Andreas and the San Jacinto fault systems approach each other, is structured in a way that does not rule out a rupture propagating across that junction and engaging both systems in a single extended event. Cascading ruptures are not theoretical constructs invented for worst-case modeling exercises. They are documented in the geological record. The 2016 Kaikoura earthquake in New Zealand is one of the most studied examples in recent history where a rupture propagated across multiple fault segments in sequence, producing an event far larger than any individual segment could have generated. The physics that allowed that to happen in New Zealand are present in the Southern California fault network in 2026. The last magnitude 7.0 or greater earthquake anywhere in California was Ridgecrest in July of 2019. 7 years have passed since that event, 7 years during which the Pacific and North American plates have continued their relative motion at several centimeters per year along every locked section of the San Andreas system. That motion does not pause. It does not negotiate. It accumulates quietly and continuously in the elastic deformation of the rocks on either side of the fault zone until the accumulated strain exceeds the frictional strength holding the fault locked. At that point, the fault moves. The stored elastic energy converts instantaneously into seismic waves, heat, and permanent ground displacement. The only variable the physics leaves genuinely open is when. 7 years of continued plate motion since the last major California earthquake. 169 years since the last major Southern San Andreas rupture. 1,000-year stress maximum confirmed by independent scientific analysis. A fault in the north moving faster than hazard models reflected. 3 earthquake swarms in less than 2 months tracing a spatially coherent path along the connecting fault corridor. A historically silent fault showing its first recorded creep after 2019, and now experiencing repeated swarm activations along its trajectory. An extraordinarily active Pacific generating typhoons, hurricanes, and tropical systems simultaneously. Back-to-back M-class solar flares with Earth-directed sunspot regions primed for further activity. A humid heat dome sitting over Southern California during a period of elevated gravitational tidal loading. Every single one of these conditions is real, documented, and measurable. And every single one of them is present simultaneously right now. This does not mean a catastrophic earthquake will occur tomorrow. Earthquake prediction at the level of specific dates and times remains beyond what science can deliver, and anyone who tells you otherwise is not being honest with you. What earthquake science can deliver is hazard assessment, the probability that the conditions are ripe for a major event. And hazard assessment is not prediction. It is the rigorous quantitative evaluation of every measurable parameter that determines how close to rupture a fault system is operating. Right now, by every parameter available to the scientific community, that assessment is pointing in one direction. The Southern California fault network is operating closer to rupture conditions than it has at any point in the modern era of seismological observation. That is not an opinion. It is the direct implication of the 2 studies published this summer, confirmed by the swarm activity currently unfolding in real time in the same fault corridor in the same weeks those studies appeared. What that means for the tens of millions of people who live within shaking distance of these fault systems is a question that goes beyond seismology. It enters the domain of personal preparedness, community resilience, and honest acknowledgement of a risk that California has historically treated as a background fact of life, rather than an active, urgent priority: emergency preparedness. Specialists consistently recommend a minimum 3-day supply of clean water at 1 gallon per person per day as a baseline household reserve. For a major San Andreas event producing widespread infrastructure damage, 3 days is not sufficient. The realistic planning window for restoration of water service, power, and road access, following a magnitude 7.5 or greater event in a densely populated corridor, is measured in weeks, not days. A 2-week minimum water reserve, secured in sealed containers and rotated regularly, is a more honest target for households within the shaking radius of any of the major fault systems currently under elevated stress. Water heaters should be strapped to wall studs using approved seismic restraint hardware. This is one of the highest value preparedness actions available to any California household because an unrestrained water heater in a major earthquake becomes a projectile, a gas leak source, and the first thing that eliminates your emergency water reserve simultaneously. Heavy furniture, bookshelves, and appliances should be anchored. Know the location of your gas shutoff valve and own the wrench required to operate it, because a post-earthquake gas leak that ignites is responsible for a significant portion of the fire damage that follows major seismic events in urban areas. The 1906 San Francisco earthquake killed more people through the fires it triggered than through the shaking itself. None of this is new information. Emergency preparedness. Professionals have been delivering these recommendations for years. What is new is the context surrounding them in August of 2026. The Coso Volcanic Field swarm is still active as this video reaches you. The Garlock Fault corridor has hosted 3 sequential earthquake swarms in under 60 days. 2 independent research teams have published findings this summer that independently conclude the San Andreas system is more dangerous than the models previously reflected. The stress load on the southern section has reached a level that scientific record has not seen in a millennium. The northern section is accumulating strain faster than hazard frameworks assumed, and the broader Pacific and atmospheric environment is contributing a convergence of additional loading variables onto a system that is already at a measured extreme. The Earth is communicating through the only language it has, seismic sequences. Fault. Creep. Stress accumulation. Scientific instruments are reading that language with greater precision than at any prior point in human history. And what they are reading right now, in this specific moment, in this specific fault system, is worth taking seriously. Not with panic. Panic is not useful and it is not warranted by honest science, but with the kind of clear-eyed acknowledgement, multi-million-year history. It will rupture again. The only variable is whether the people and communities in its path are meaningfully more prepared when it does than they would have been without paying attention to the signals the system is sending right now. That preparation is a choice that can be made today, before the event, when the cost of making it is low and the benefit of having made it will be immeasurable. The Coso swarm is still running. The Garlock corridor is still loaded. The science published this summer is not going away. Keep watching this situation, because the progression from Fraser Park to Johannesburg to Coso has not announced where it ends. And every serious geologist monitoring the system right now is asking the same question about what comes next.